And so let's give them. So we know some rules for exponentials. Well, let's start by just writing down what the log laws will let us do. So this one you already know. If you have a logarithm with absolutely any base, then what is the log base? Yeah.
You wouldn't have any values.
Say again? I definitely do, but they are upstairs. So unfortunately today, I guess you are stuck taking notes on normal paper. I think it'll be okay. So the stuff on this page is somehow the most important stuff, and then we'll do some stuff with it. So let's start with something you already know. What's the log base b of 1? Say it louder. 0. And let's talk about y. Let's talk about y. Let's try to figure out what goes in that star. Is that an equation you could rewrite in exponential form? What would you get in exponential form? Yeah, perfect. What power do you need to raise b to in order to get 1? 0. And this is the same logic as will apply for all the rest of the rules. Exponentials satisfy rules. Logs will satisfy somehow the inverses of those rules. So let's say what the rest of them will be. So the first logarithm law says that the log of a product is equal to something. The log of a quotient is equal to something. The log of a power is equal to something. So those are, if you like, the main logarithm laws to think about. And each of them will come from exponential laws. For any base b, b to the 0 is equal to 1. And this had a lot to do with that. They're in some sense the exact same fact, those two underlined in pink. So let's start listing some other rules. The product of exponentials. What's b to the x times b to the y equal to? B to the x plus y, right? If I have x b's and multiplied together, and then I have y more b's all multiplied together, they're a total of x plus y. What about b to the x divided by b to the y? B to the x minus y, right? If you like, a bunch of the powers of b will cancel. And what is b to the x to the y? Yeah. So each of these three rules will give us something in the language of those rules. And we'll see exactly what they are. So first, let's think about the log base b of x times y. So let's try to compute log base b of x times y. We expect our answer to have something to do with the log base b of x and the log base b of y. So what I'll do is I'll write down, I'll give names to the log base b of x and log base b of y. And then I'll see what I can do with log base b of x and log base b of y in order to get log base b of x times y. So let's get the names. What would you like to call the log base b of x? Give me a variable name.
A.
Cool. I'll use capital A. Don't know if that's what you meant. That's what I'll use. What would you like to call the log base b of y?
C.
I see that you're avoiding the letter b for a reason. That works. So that gives me two equations, doesn't it? Log base b of x equals a, log base b of y equals c. And here's the power of just giving something a name. Once you give something a name, you can start manipulating equations. If you want to rewrite this in exponential form, what would you get? B to the a is equal to?
X.
Yes. X equals b to the power of a. And what about y?
Y equals B to the C.
b to the c. Oh, okay, I see now why you left out the x is equal to, because it was already there. And that's illegible now. Y equals b to the c. So I know what x is. I know what y is. I'd like to know what log base b of x times y is. So let's do that by just thinking about x times y. What's x times y equal to if this is x and that is y? Well, on the one. Yeah. Because there's what it is by just plugging in, by just substituting. And what's b to the a times b to the c? Nice. All right, so I'm going to rewrite that again. X times y equals b to the a plus c. Does that look like an equation that is currently in exponential form? What happens when you rewrite it in logarithmic form? Let's start with what it is in log form. What's the base in that exponent? B. So that'll be the thing in the base of the logarithm. What'll be the thing inside of the parentheses of that log? Just the stuff on the opposite side of the equal sign, right? And it will be equal to the stuff in the exponent, a plus c. So the log base b of xy is equal to a plus c. And now let's go back. What is a equal to?
Log of x of b.
What is c equal to?
B.
Nice. So that means the log base b of x times y is equal to the log base b of x plus the log base b of y. Hey, is that one of the formulas we wanted? At the top of the page? Yeah, let's fill that in. So here is a fact that you now know. Log base b of xy is log base b x plus log base b of y. Feel pretty okay? So here's the rough outline of what we're going to do with each of these three. We'll talk a little bit about where the formulas come from. We'll write down the formulas, and we will use them to get some results. So, we've just written down one of the formulas. Let's use it to do some stuff. So, let's use it to do these, in fact. Let's compute the log base 3 of 2 plus the log base 3 of 1.5 without using a machine. So the first thing to notice is I can't compute log base 3 of 2 without a machine. I know it'll be less than 1 because 2 is less than 3, but it'll be bigger than 0. That's all I know. Same thing with 1.5. So let's try to take these two things, study them, and figure out what the sum will be. So is that a sum of two logs? They both have the same base? So what does the logarithm law say this should be equal to? Log base 3 of 2, not plus, but times 1.5. So I'll put these on the board so I can use them later. So one of the rules was log base b of a product becomes the sum of the logs. Nice. And now let's do that. What's 2 times 1.5? 3. So this is the log base 3 of 3. What's the log base 3 of 3? 1. Nice. Oh, and now maybe is a good time to point out the following. So there is a quiz this coming Friday, the end of the week. So let's see, did people get a notification that I put up this survey to fill out? My intent is that people wouldn't fill it out if they are planning on coming to class, but the instructions are not very clear. And lots of people have already, which is fine, but now I'm telling you not to. So the thing that I'm pointing out now, because it's relevant, is there is a sample posted for that quiz. Does that problem look kind of like it's similar to this problem? Yeah. So the ideas I'm doing today will come up on that quiz. There's something to think about. There's also solutions to that sample posted. So we can also use this to solve equations. Let's try to solve that equation. Log base 3 of x plus the log base 3 of x plus 8 is equal to 2. So when you look at that, you say, well, it's annoying that there's more than one log inside. If we were just log of thing is equal to number, you could rewrite it in exponential form. And the problem would become easier. You can get rid of the log. But this doesn't have one log, it has two. Can that rule that you rewrite it so there's only one log? Yeah, let's do exactly that. So I see here a sum. Log will turn a sum outside of the logs to a product inside. So it'll become log base 3 of x multiplied by x plus 8 equals 2. All right, so now there's only one log. What seems like a good move to do next?
Distribute? Or no?
Sure, you just mean the x times x plus 8?
Yeah.
Yeah, we may as well. And it's still inside of a log. All right. What would you want to do next? Let's put it in exponential form. So, color coding a little bit. I see the base is 3, so I will see 3 to the power 2 equals the stuff that was in the parentheses. I guess 3 squared is equal to 9, so. That look like an equation that's easy to solve? There will be a subtlety in the final step, so I think I want to go through the rest of the walk. What do you need to do to solve? What would you want to do to solve that?
Move the 9 over.
Move the 9 over. X squared plus 8x minus 9 equals 0. And next.
Factor the quadratic formula.
Yeah. So you said like the name of two different strategies. We could factor or we could use the quadratic formula. How many people would be tempted to try to factor? How many people would rather use the quadratic formula? How many people would try to complete the square? All right. Cool. So those of you who are factoring it, what do you get it to factor as? X minus 1, x plus 9, right? Okay. All right, so you need two things that multiply together to be 9. 1 times 9 is 9. One of them's negative, so it's negative. And then they need to add together. 9 minus 1 is 8. So yeah, that works out. So what is x? Cool. And there's one last subtlety I want to point out. So we found two answers. Let's see if both of them are actual answers. And this double check is something that I often don't do in class, but there's something weird that's about to happen. So let's try to plug these in and see what happens. So let's think in particular about domain. So let's try to plug in x equals 1. If we do that, we'll get the log base 3 of 1 plus the log base 3 of 1 plus 8. And make, we can actually walk that out the rest of the way. What's the log base 3 of 1?
0.
0. Log base anything of 1 is 0. What's the log base 3 of 1 plus 8? So I guess walk it out from the inside out. 1 plus 8 is 9. Is 9 a power of 3? Cool. So that's log base 3 of 3 to the power 2. What is that equal to? So remember, logs undo exponentials. So the log base 3 and the 3 to the power will undo each other, leaving you with 2. So the whole thing is 2. Is that what it's supposed to be? Nice. That's good. Let's plug in x equal to -9 and see what happens. Log base 3 of -9 plus log base 3 of, well, that. Is anything wrong with that? Yeah, there are negative numbers inside of the log. That is not allowed. Negatives are in log. This is not even in the domain. Negative in log. So this is not in the domain. So is x equal to -9 actually a solution to the equation? And here is why. So there have been lots of examples where we've seen that if you change a function by doing some algebra to it, you might accidentally change the domain. That's exactly what happened here. Here, if you try to plug in x equals -9, you get 2 negatives inside of a log. But if you do this algebraic manipulation, you get a negative times a negative, which is positive. This has bigger domain than the original problem. So the big thing is, here's the caution. Check that your solutions are in the domain of the starting function. And that triangle is supposed to be like a caution sign. That idea make sense? So I think I'll hit the next 2 log laws more quickly. I'll state them and then we'll use them. So if logs turn multiplication into addition, what do you think they turn division into? Yeah. Log base b of x over y is the same as the log base b of x minus the log base b of y. So there's the second rule. I'll write it down straight away. And I guess it should go on the front page too, for the sake of having notes that are complete. So instead of going through the derivation, which will be basically the same as what we did to get the formula for products, let's use it instead. So let's try to compute log base 5 of 15 minus log base 5 of 30. So again, 15 isn't the power of 30, so I can't directly compute log base 5 of 15. 30 isn't the power of 5, so I can't directly compute log base 5 of 30. But what will log turn that subtraction into? Division. Subtraction outside of the parentheses becomes division inside of the logs. Log base 5 of 15 divided by 3. And now let's go and keep simplifying. What's 15 over 3? 5. So this becomes the log base 5 of 5, which is equal to 1. Nice. We can use this property also to solve equations. And let's try to do that. Let's try to solve log base 2 of x plus 2 minus log base 2 of x plus 1 equals 3. Cool. So let's just check one thing for us. Both of those logs have the same base, I hope. Nice. So let's try to use the same rules. What will that subtraction, well, I mean, maybe I'll give you a choice. Should I just pause for a moment and let you all do it on your own, or should I keep talking? Should I keep talking? Okay, I'll be quiet for a second. You will find the answer. Once you come down to a solution, go ahead and discuss it with each other. Well, discuss before you even have a solution if you want to talk to each other about it. Cool. What are we getting?
I got negative 6/7.
All right. Does that agree? People want me to talk to it? Cool. So, was that a head? Yes? I didn't see any. I think I saw a head nod, but no hands are up. Okay. Cool. So I'm going to add one quick check. So how many people actually checked that this was in the domain of the original problem? It might be worth doing, especially because it looks negative. So let's just do the quick check. If that isn't in the domain, then this equation has no solutions. So the options are either this is the solution or there are none. Let's see if this is actually a solution. So let's plug in 6/7, see what happens. We'll end up with log base 2 of negative 6/7 plus 2 minus log of 6/7 minus 1. And I don't think I want to go all the way to checking that this is equal to 3. Instead, I'll be happy if I can just convince myself that the thing inside of the parentheses are positive. Minus 6/7 plus 2, is that positive? Yeah, right. This is less than 1, that's bigger than 1. I guess you could walk out that it's like actually equal to, what, 8/7 when you do the subtraction? But all I care about is it's positive. Same thing, is this actually positive? Let's see, 1 is like, well, it's not positive because I wrote it down a little bit.
Negative 6/7, yeah.
Now, is it positive? Yeah, cool. So it's actually in the domain. Nice. So carrying on. So far we have the rule for what log does to multiplication. It demotes it to addition. It devotes division to subtraction. So what do you think exponentiation will happen? What will happen to exponentiation? Become multiplication. In fact, it will become the log base b of x multiplied by y. No logs around the y anymore. So, because I want to get to some other examples and applications of this, well, I don't know, do people want me to go through the argument for why it's true? Okay, it really is the same again. Let the log base b of x be a thing, give it a name, and then rewrite it in log form and figure out what x to the y is equal to. So we can use this. I should put it on that front page again. So, in grad school, I had a colleague who had the following as his way of enjoying talking about logs. So, this person was also an irresponsible cyclist. And so his analogy was as follows. So logs take an operation and demote it to something that's a little bit less intense. And that was his philosophy with being a cyclist too. A cyclist takes a stop sign and really replaces it with a yield sign. A cyclist takes a stoplight and really just replaces it with a stop sign. Don't do that. That's bad advice, and it's, a good way to get yourself hit by a car and then to not be eligible for that car being liable for the damage they do to you. All right, cool. So, with that analogy, which is, I think, fundamentally bad, out of the way, let's do some stuff with these rules. So let's start by this. I don't know if we'll go all the way through solving this equation unless people want to. We'll at least start through the process then. So that's an equation where I see multiple logs floating around with some things next to them. As is, that's a little bit annoying to try to solve. If I could rewrite it as a single log equals a thing, then I could use log laws to solve it. So let's at least get to the point where we've used the logarithm law to get rid of the logs and get done something algebraic. Cool. So there is an expression. Do you see an application of a logarithm law directly to that? Yeah, what do you see?
You can move the 2 back into the log.
Yeah, this is a number times a log. A number times a log is log of a power. So this will be the same as the log base 5 of x plus 1 squared minus log base 5 of x minus 1. All right. Do you see another logarithm law that lets you do something? Yeah, what do you see?
Do division.
Yeah, subtraction will become division. So I end up with the log base 5 of x plus 1 quantity squared over x minus 1. Oh, and this is all equal to 2. I can't just ignore the other side of the equal sign if I hope to solve the equation. All right. Does that look like something you could rewrite in exponential form and hopefully it would be nicer looking? Yeah. What's the base? You would raise it to the power. And that is equal to the stuff inside of the parentheses, x plus 1 squared over x minus 1 equals 5 squared, which is 25. Nice. So we are now at this point. X plus 1 squared over x minus 1 is equal to 25. And I guess first question is, does that now look like an equation that is easier to solve than the one we started with? It looks like a rational equation. So a rational function equals a number. We have a strategy. And now's the point where I'll see if people think it's worth the time to solve it. Do people want to spend time solving that? Is there demand? Cool, I will. So what would you do? I guess you would cross multiply. All right, that would get rid of the division. Maybe you would also FOIL. And then I think you just set yourself up to use the quadratic formula. Cool. All right. So now is a slightly embarrassing typographical thing that I intended to remove before printing these. That was a note to me while I was revising the notes from last year. A note that I was intending to do a revision, which I did, but that I didn't take out the note about the revision. So here's the last couple of laws that I want to hit are the change of base formula for exponentials, which will say that if you know what one exponential looks like, then you can understand every exponential as long as you're okay with introducing a log. That's a rule that's very important once you hit calculus. You'll want to start thinking about everything as the natural exponential, and this is the rule that you use to do that. You can also do the same for logs, which we stated the formula last time. If you know how to compute with one base in a logarithm, say log base 10 or log base e, then you can really work with absolutely any base. And let's talk about why. So let's try to do that. So the change of base formula will say that a to the k is equal to your favorite base to a constant times k, where that constant is something. And you know what? Let's actually just try to solve that equation for k. So let's try to get k on its own. So there's the thing I'd like to find. I'd like to find k. All right, so here's the way I'll think of this. This is an exponential equation. It's an exponential equation in like two different ways. It's a to a power equals a number. It's also b to a power equals a number. I think I want to think of it the second way. B to a power equals a number. I can rewrite that in logarithmic form to get oh, there's another embarrassing typo. Any other exponential can't be written. So do that. Log base b of a to the x equals k times x. Did I rewrite it in log form correctly? Cool. Do you see any logarithm laws that might be helpful here? What do you see? Take x out, put it as a multiplication. Log base b of a times x equals k times x. And remember, we want to get k on its own. We want to solve this for k. So what should you do next? Divide both sides by x. That will effectively cancel the x's. Okay, do we know what k is now? There's the change of base formula for exponentials. Or rather, there's why it's true. Here's what it says. The exponential formula for, the change of base formula for exponential says that for any base b, a, and your favorite base b, a to the x can be written as something in terms of b to the x, as b to that constant, log base b of a times x. So if someone hands you an exponential and you don't want to work in terms of that exponential, here's how to change to the exponential you'd rather work in terms of. I guess this can also be interpreted as follows. Log base b of a, you should think of that as being a constant. That means a to the x, the graph is going to look exactly like b to the x, just either stretched horizontally or shrunk horizontally. That seem okay? So let's use it to just re-express one thing. Let's rewrite, let's just do one of them, pi to the x in terms of e to the x. So let's try to rewrite pi to the x. So let's just try to match up symbols. What is a, what is b, and I guess what is x? Well, x is x. So let's just try to rewrite a and b. So this is how to re-express a power of a as a power of b. So I want to rewrite a power of pi as a power of e. Oh, cool. So what should I set? What should I use as a? What should I use as b? Nice. Okay. That means pi to the x is equal to. So here's a. So there's a to the x is equal to b to the log base b of a times x. Pi to the x is equal to e to the log base e is ln of pi times x. Cool. And that's a formula that really comes into its own in terms of its power once you hit differential calculus. Because then that tells you e to the x is something that you do a lot of things with very easily in calculus. This says that if you can do things with e to the x, you can also do it with any other exponential. Neat. All right, so jumping down to halfway through this page. Okay, well, no, let's do this example too. So here's the graph of 3 to the x and 2 to the x. Let's just see, I said something about there being a horizontal or vertical, a horizontal compression or stretch. Let's see if this actually holds up. So this says, the change of basis formula says that 2 to the x is the same as 3 to the log base 3 of 2 times x. And right here, the log base 3 of 2 are somewhere around 0.63. Now let's see if this actually seems right. So that means that if you want 2 to the x, you start with the graph of 3 to the x, and then compress by a factor of 0.63. Well, compression by something that's less than 1 is really a stretch. Does the graph of 2 to the x actually look like a horizontal stretch of 3 to the x? Yeah. That checks out. And again, stretch always looks wrong when I spell it. That's how you spell stretch, right? Okay, good. Yeah, that's what makes me confused.
I get confused too if there's an extra T.
Okay. Well, at the end fun, but I also really want to put an A in there. Yeah, I'm like, when you say it that way, it's obviously wrong. So there's one last formula I want to do. I want to say there's some way of taking a log that you know and using it to express absolutely any log. So let's do that. So let's start with this. What is a to the log base a of x? Remember, logs and exponentials undo each other. Should be exactly x. And I'm going to do something that will seem like a really weird thing to do, but we'll see something useful come out of this. I'm going to apply log base b to both sides of this equation. I'm not telling you why I'm going to do it, but certainly whenever you see two things that are equal, you can take the log of both sides and those will still be equal. So, right, there are always two questions. Should you do something? Can you do something? I'm not going to try to convince you that I should. I'm going to do it anyway. And you can, because you can always do the same thing to both sides with the equal sign. So we get log base b of a, maybe there will be some color coding showing up, log base A of x equals log base B of x. And if you look at the goal, I want to know what the log base A of x is equal to. Does that complicated thing look like maybe I could solve it for the thing in pink? Yeah, what seems like a thing you could do to, I don't know, simplify that a little bit at least? Do I see an exponential inside of a log? So I can use this rule. Let's use that rule. I guess that means that I can take the pink thing out of the parentheses and just put it next to that expression as a multiplication. All right, and if you wanted to solve for the thing in pink, what would you do? Well, division would do the trick, right? Yeah, see, a thing times the thing in pink is equal to a thing. Let's just divide one of those things to the other side. So the log base A of x is equal to log base B of x divided by the log base B of A. So there's the change of base following up a logarithm. So whenever you see a log with a base in it that you would rather not see, you can switch to a base that you do like by using this division rule. Log base A of x is equal to the log base B of x divided by the log base B of A. I think the two things that I want to do with this today is, one, do that example that's right below, and then do a problem that's an awful lot like something that's on the homework for today. So, first things first. If we express the log base 3 of x in terms of the log base 10 of x. So I want to express the log base 3 of x in terms of something involving the log base 10. This theorem says that you can express the log base A of x in terms of the log base B of x by using this rule. So, what should I use for A? What's the base that I want to get rid of? 3. So I will use that as A. What should I use for B? 10. 10 is the base that I want to see at the end of the day. So that's the log base B of x divided by the log base B of A. That idea seem pretty okay? Cool. So if, say, on some sort of homework or example, I have you do something that makes you want to compute a logarithm with some base other than 10, and maybe your calculator is a calculator that you've only figured out how to work in base 10, does that let you work with respect to any base you want? Yeah. Whenever you see a base you don't know how to work in terms of, as long as you can do division, you can live with it. So here I think is the last thing that I want to do. Let's try to compute something that's kind of complicated. Is this on this page? Yeah, in fact, I think here's the thing I want to do. Let's try to compute this. Log base 2 of 3 times log base 3 of 2. Let's try to figure out what that is equal to. let's see, is this one where there's multiple bases floating around for those logs? Could I rewrite this using a single base? In fact, I could use any single base I want. What base would you want to use? Oh. Yeah, this literally was a problem where there was no, well, a wrong answer would have been like 1. You can't use 1 as a base. And like a negative would probably have been bad too. But yeah, let's use 10. So let's re-express with respect to base 10. All right, so maybe I should have put the rule here. Log base A of x all right, so let's start with this log base 2 of 3. So if I want to re-express log base 2 of 3, what should I use for A? So if I want to get rid of the 2, this lets me say instead of having a 2 in the base, I can have it be like a 2 in the denominator and a 10 in the base, since we're deciding to use base 10. That's the same thing as, let's come up here, log base 10 of 3 divided by log base 10 of 2 times log base 3 of 2. So what should, well, maybe just this. What will that turn into? Let's see, it'll be some division. So what should be the thing in the top? It should be the thing in the parentheses. Log base A of x. The thing in the parentheses becomes the thing in the parentheses in the top. What should go in the bottom? Nice. So on the one hand, there's like the computation, but does that simplify now that we've written it down? What's that equal to? This and this cancel, this and that cancel. Cool. So I guess I'm out of time. And maybe I'll give you this string of words verbatim to think about if you go right to the homework after the class. So thinking about the open-ended for today, this idea is the only thing you need.